This tutorial is entitled Transient Analysis 2 and will make use of the same simple RC circuit utilized in the previous tutorial. However, there is one major difference. In this case, the input is a sinusoidal waveform, the AC signal, AC voltage waveform. It's been set to 100 volts peak at a frequency of 1 kilohertz and 0 degrees. Now that 0 degrees represents the fact that it is a basic sine function. Let's take a look at the window describing the parameters for AC voltage. We have the peak value here, 100 volts. There is no offset. That would be a DC value that you add to the input signal. So it's set at 0, the default value. The frequency is 1 kilohertz. Note the tab over here where you can set kilohertz, megahertz, or whatever. There is no time delay. And all the parameters from here on down, other than the phase angle and possibly the damping factor, the phase is 0 degrees. And that represents the reference phase for a sine function. And that is an interesting thing to point out as we go along. The rest of this is more concerned with frequency response type analysis. So these are the major parameters for the transient analysis with a sine function are up here. So let's click OK. And I should note that this circuit could be analyzed for the AC steady state response by using the J operator form, in which case this impedance would turn out to be about minus J 159 ohms. And so that magnitude is smaller than 1K. So you'll get a smaller voltage across here, a much smaller voltage than the 100 volts peak. At any rate, let's go ahead and do an analysis here. I'll click on the grapher and come down to transient analysis. Some parameters may already have been set. The way this would come out initially would be the automatically determine initial conditions. This is the way when you first set the circuit up, it comes out automatically determine initial conditions. Now I will say that because the sine function is 0 at t equals 0, you could actually use that particular operation for this circuit. However, whenever you have anything that could cause a voltage to exist across the capacitor at t equals 0, it's probably better to go to the set automatically, setting here, set to 0. If you want the voltage on the capacitor and if you had an inductor, current through the inductor to be 0, you would set it to 0. Once again, we could have gotten by with the automatic in this case because of the fact that you have a sine function and its value at t equals 0 is 0. But in general, it's probably better to use the set to 0 whenever there's any chance, especially if you have complex waveforms or a phase angle other than 0. You should definitely go to this parameter here if you want the voltages on capacitors to start at 0 and the currents through inductors to start at 0. Now I'll set that to 0 then, and the time range here is from 0 to 5 milliseconds based on the fact that the time constant is 1 millisecond. We have 5 time constants. And if we start out with the generate time steps, this would have been the default, generate time steps automatically. Let's take a look and see what we get. Okay, it is starting at 0 as you expect, and we have the natural or transient response in this interval, and it reaches steady state after about 5 time constants. However, while the results may not be very far off, in fact they're pretty close, it's not a very good looking sine wave because you see that jagged nature here at the top of it. That suggests that maybe we should go in and use another option besides the default of accepting the to generate its own time steps. So again, we have a kind of a jagged sine wave. So I'm going to go back and do that again. Transient analysis. And this time I'm going to use the option of maximum time step. Now you can use minimum number of time points. That works very well as well. I'm more used to using maximum time step, so I think I'll use that. And a rule of thumb that I have is that you should have about 100 points minimum per cycle at the highest frequency if possible. Sometimes that's not very practical, and in some cases you may have to even use a smaller time step. But at any rate, I'm going to put it at a maximum time step, and I think this value was left from a previous run, but I'm going to enter it as 10. Well, first of all, maybe we should calculate it. To calculate it, we note that the frequency is 1 kilohertz. That corresponds to a period of 1 millisecond. So if we want to have 100 steps per cycle, we would have 1/100th of 1 millisecond, which is 10 microseconds. So I'm entering that as 10e minus 6. And then I'm going to hit simulate. Well, we generate the same signal, but we have a much smoother representation. Now, I have checked, and the previous run in which you allow it to set its own time step is not very far off. It's pretty accurate. This is a little bit more accurate. It's just a matter of checking for a given waveform. I won't do this, but I always recommend, if you have any doubts, to maybe take runs at 2 different time steps and compare values. That takes a little time, so I'm not going to do that. But one thing one could do is go back and use 1 microsecond and run a transient on it, and then check some values like peak values or zero crossings or whatever, and see if you get the same results. And so if you use 2 different time steps and get the same results, chances are pretty good that you're okay. All right, now I'd like to illustrate one more thing before I go any further. I would like to look at this in steady state. Suppose I just want to generate a steady state response for this circuit. Well, let's go back to transient analysis again. We're going to leave our time step at 10 microseconds. But what you want to do in this particular case is actually use a start time after you can assume that steady state conditions have been met. So for example, we know at about 5 time constants that for most practical purposes steady state has been reached. So let's enter that as 5e minus 3 and set the final value at 10e minus 3. In other words, I'm going to have the same range of time from 5 to 10 as I had before, from 0 to 5, the same number of cycles. And we again have our maximum time step, and we've set the initial condition to 0. So let's do a simulate. And what you have here is the steady state AC response. Even though the title of it is transient analysis, we've actually skipped over the first part of it. We have, since the total response is generated if you start from 0 and run it out far enough, if you start after steady state has been reached, then what you see is the steady state response. And in fact, if we went back and used steady state AC analysis to calculate what the phase lag or lead or whatever, in this case it'd be a phase lag, the voltage on the capacitor, you can actually probably assume this point to be equivalent to 0 because it's an integer number of cycles from the beginning, and you see that there is a phase lag of the output voltage. So this illustrates the process involved with a waveform, in this case a sinusoid, Now let me just do one more thing before I complete this. I would like to put a larger value on the capacitor. I think, I guess I must have already set this at 25. It'll probably be a default of 0, but you can set it to whatever you want to here. I'm going to set it at 25. This is going to force the initial voltage on the capacitor to be 25 volts. So let's click OK on that, and then go back to the transient analysis. But remember, I changed the time here, so I'm going to make that 0 to 5 milliseconds again, 5e minus 3, and on the maximum time step is OK, so I hit simulate. Well, you see an even more pronounced transient response in this case, because it started at 25 volts and it peaked way up here at over 40 volts, and then it continues until it settles down along in this range here. It's reached pretty much steady state at this point. So this concludes this particular presentation with a sinusoidal input voltage to a simple RC circuit.